Okay, yes. Hi, everyone. Welcome to GOCC. We're very happy to have Robbie Angarone, or as Vic Reiner said, our own Angarone, speaking to us today. Before we get started, I'm just going to remind us of our community statement. It's that we're all learning, everyone has something to contribute, and no one has all the answers. Take it away, Robbie.
Okay. Hi, everyone. Yeah, my name is Robbie Angarone. I do pronounce it with the E at the end. Thanks to the organizers of the GOCC for inviting me to talk about cylindrical networks and total positivity. So this is something I've been working on for a while, and I actually wanted to give you a little bit of a note at the start. There's a version of this work on the archive right now, but what I'm about to talk to you about is a very different version of that work. And that's because basically in the original version, when I tried to submit it to FIPSAC, an anonymous reviewer told me my result was already known, which is disappointing at first. But I realized that since my proof technique was novel, I was actually able to push the result further than it had been before. So this is a little message to not give up. It can be very discouraging to discover your result has already been proven. But since you're a new person, you probably have some amount of new perspective. And that means your techniques might just be able to get you somewhere new as well. So let's talk about what's going to happen in this talk. So I'm going to start with talking about totally non-negative matrices and the Gessel-Lindström-Viennot lemma, which some of you may have heard of before. It's very classical stuff. But then I'm going to move into a generalization of this story, which takes place in something called the loop group and involves cylindrical networks rather than planar networks, as in the usual story. So I'm going to explain what exactly my result in this world is, and then I'll talk for a bit about my proof technique, which to me is the cool part. So let's get started. So a totally non-negative matrix is a real matrix with the following property. If you take a square submatrix, its determinant is positive or non-negative if the matrix is totally non-negative. Here's an example. Here's a non-example. You'll notice that in this middle example, if you tried to take a consecutive submatrix or minor, as I'm going to refer to them a lot in this talk, like the top left 2x2 block, it has determinant 0. So it might seem fine, but we include minors which are not consecutive in rows or columns. So this matrix has a negative 2x2 minor. We don't count it. Here's a totally positive matrix. All of its minors, including the entries alone are minors, are strictly positive. And it's a classical theorem that the set of invertible square totally non-negative matrices are closed as multiplication and form a semigroup whose generators can be described very simply. The generators are sometimes called elementary Jacobi matrices or Chevalley generators. They're basically identity matrices, but they differ from the identity matrix in just one spot. So in the leftmost one, there's a diagonal entry, which is some other positive number. In the middle one, there's an entry just above the diagonal, which is some other positive number. And in the one on the right, there's an entry just below the diagonal, which is some other positive number. So these, when you take products of them, you can get to any invertible totally non-negative matrix. Okay. So how does this have anything to do with networks or combinatorics? It's not obvious from the outset. So for me today, a network is going to be my shorthand for a planar, acyclic, edge-weighted, directed graph. I don't want to say all those adjectives, so I am going to call something with all of those things a network. For example, this. By default, I'm going to organize all of the sources of the network on the left-hand side of the matrix, and all of the sinks of the network on the right-hand side of the network. And also by default, any edge which is unlabeled has weight 1. So you can see here I've given some of them some integer weights, but the rest have weight 1. Now to any such matrix, we can associate a graph, which I'm going to call to any such graph, we can associate a matrix, which I'm going to call the weight matrix. What does the weight matrix do? Well, its ijth entry tells you about paths which go from the ith source to the jth sink. And the numbering is in such a way that on the left here, the topmost source is the first one. Then the next one down is the second one, and so on. And on the right, the topmost sink is sink 1, then sink 2, then sink 3. So if we were to make this matrix, in this case, it would look like this. So let's explain, for example, why is the 1, 1 entry equal to 8? Well, it should tell me about all possible paths which start at the first source. That's this one. You can all see my mouse, right? Okay, good. So it starts at the first source, which is this one, and should end at the first sink, which is this one. Well, there's this path which goes straight across. That has weight 1. We take the products of the edges in the path, the edge weights in the path. Then there's this one which sort of goes down in a trapezoid, then comes back up. That has weight 1. Then there's this path which comes down in a larger trapezoid and comes back up. That one has weight 6 because the path had a bunch of edges of weight 1 and another one of it weight 6 for a total of 6. And when you add that to the other two paths, you get 8. As another example, the 3, 1 entry is 0 because there is no way to get from the third source down here back up to the first sink. So that entry is 0. There are no paths. Okay, so that's cool. That's a way to take a graph and get a matrix. What does it have to do with total positivity? Well, let's make a couple of observations. The Gessel-Lindström-Viennot lemma itself tells you what happens if you start with a network, then create the matrix, and then take a minor of it. In other words, a determinant of a square submatrix. The lemma tells you that if you take such a minor, you're going to end up with a generating function for now families of non-crossing paths rather than single paths, whose sources are in your row set capital I, and whose sinks are in your column set capital J. So let's do an example. Here's our network again. And here's a minor I could take. This top 2 by 2 should be telling me about paths that start at source 1 and sink 1 and end, source 1 and source 2, and end at sink 1 and sink 2 and don't cross. The claim is that this should be counted by 8 times 4 minus 7 times 1. How can you see it happening? Well, I claim that, let's draw here all the possible paths from source 2 to sink 2 in blue, and all the paths from source 1 to sink 1 in red. This 8 times 4 is basically telling you the number of ways, a weighted count of the number of pairs of paths. Independently choose one of the red paths and one of the blue ones. But then we have to subtract off all the possible crossing pairs of paths. Namely, if I chose this topmost blue path, for example, and the bottommost red path, that would be a bad choice because they touch. We don't want them to touch at all. That's what we mean by crossing. In fact, there are 2 ways that could happen. One's with weight 6, and again with weight 1. So we subtract off 7 to account for all the possible crossing families. And the content of the Gessel-Lindström-Viennot lemma is that determinants always cancel out perfectly so that you are left only with the non-crossing families of paths with a given row set and column set. As a corollary, we get that any network with positive edge weights is totally gives rise to a totally non-negative weight matrix because the entries and the minors are all just sums of products of the weights, which by assumption are positive numbers. So that's kind of cool. I showed you a specific kind of graph, and I told you that if you create a certain kind of matrix from that graph, it will be totally non-negative. Maybe you're not that impressed because it seems kind of like I just constructed the matrix in precisely such a way that it would be totally non-negative. The really cool thing is that it goes the other way. So to see that, we need a couple of lemmas. The first is that concatenation of networks corresponds to multiplication of the weight matrices. So if I take 2 networks like this, N1 and N2, and I stick them together so that the sinks of the first one are overlaid on the sources of the second one in one big network, then that corresponds to multiplying the matrices. If you haven't tried this as an exercise before, I recommend you do. You will sort of discover that networks and matrices are basically the same thing, but in different guises. So that's pretty cool. The next thing we need to realize is that the semi-group generators for that set of invertible, totally non-negative matrices are each representable by networks with positive weights. So for example, this one, which has a single positive entry just above the diagonal, corresponds to a network which looks like this. It has an entry in in spot I, comma, I plus 1. So we add an extra arrow going from source I to sink I plus 1 with a prescribed positive weight. And that's the network. The ones along the main diagonal are explained by the edges going straight across. Similarly, if we wanted a single weighted interesting entry just below the diagonal, we could draw a network that looks like this with the edge going up. And since we know that matrices like this give a factorization of any possible totally non-negative invertible matrix, we know that we could also just paste together these networks to represent that matrix. So the corollary here is every invertible totally non-negative matrix is representable by a network with positive weights. So in summary, what we've learned so far is that an invertible matrix is totally non-negative if and only if it's representable by a network with positive edge weights. I might stop here and ask if there are any questions about what we've seen so far. This is the sort of classical part of the story.
Yeah, sorry, I missed your definition. Sorry, go ahead.
No, please continue.
I missed your definition of non-crossing. Does it mean that they shouldn't share an edge, or they shouldn't share a vertex?
They should share nothing at all. They're allergic to each other.
Nothing at all. Got it.
I think my question belongs at the end, but because you specifically paused for questions while I was writing it down.
Okay.
So there is kind of a brute force way of constructing a network to match a weighted positive, a totally positive matrix or non-negative one. Is there a good way to morph between different networks that have the same weight matrix?
Yes. You can describe certain local moves which sort of correspond to relations among the semigroup generators. And it was studying these local moves which gave rise to the invention or discovery of cluster algebras. So yes, you can. Yes, you can study that, and it's cool. Yeah. Okay, so there is also a theorem due to Brenti, which says that any matrix with real entries, invertible or not, square or not, is totally non-negative if and only if it's representable by a network with now non-negative edge weights. This is much more difficult to prove than the invertible case, only in one direction though. So the if direction, that if you start with a network with positive weights, you get something totally non-negative, is still a direct corollary of the Gessel-Lindström-Viennot lemma. We now just consider networks where maybe the number of sources is not equal to the number of sinks. The other way around is more difficult. Brenti's proof cites a couple of other papers and is more complicated. You can't just refer to the semigroup generators because the non-invertible matrices don't form a semigroup with simple to describe generators. So it's more difficult in the other direction, but it's still possible to do. By the way, as we exit this normal part of the story, I want to mention that Rhodes and Skandera observed that actually every n by n complex matrix is representable by a network with complex edge weights, which is kind of cool. And so that really strengthens the connection and maybe would convince you that networks and matrices are kind of the same thing. The problem here is their construction wouldn't help you to prove Brenti's theorem because it doesn't, for a totally non-negative matrix in general, produce a network with non-negative edge weights. So the non-negativity of the edge weights is desirable, and that's the part that's more difficult to secure. Okay, so let's now talk about the more general context in which my result is going to take place. That's the loop group. This is going to be a weird definition, but I'm going to talk about why it makes sense in a moment. So for us today, a polynomial loop is going to be a matrix whose entries are real Laurent polynomials. And a polynomial loop into GLN is going to be a square loop whose determinant is a non-zero monomial. I'll talk about why we should call these things loops in a moment, but let me show you how I think about these things. I think about them in terms of unfoldings. So this was a notion introduced by Thomas Lam and Pylyavskyy. And the idea is that if you're given, in this case, a 3x2 matrix whose entries are Laurent polynomials, and as a reminder, Laurent polynomials are ones where you can have some negative powers of your variable, we're going to associate to such a matrix an infinite periodic matrix whose entries are now just real numbers. So let me set up my infinite grid and show you how I would make this matrix. To start, I form a periodic pattern of blocks that keep track of the constant terms. So you can see here the top left polynomial doesn't have a constant term. So the top left entry of this block that I'm tiling has a 0. The bottom right entry has 11 as its constant term, so I have 11s in the bottom right entries of these blocks. Then I do the same thing with the t terms. So for example, the 2, 1 entry has 2 as its coefficient on t, so I've put it in the 2, 1 entry of this periodic block. And I keep going. Then I make some periodic blocks which keep track of the t squared terms in this various matrices and the t cubed terms. And in this case, there are no polynomials with coefficients in degree higher than 3, so we can stop there. But we do need to keep track of the negative degree terms. So I also make a block off to the left that keeps track of the t to the -1 coefficients. And we even had a polynomial with a coefficient in degree -2. But after that, we're done. The degrees of these polynomials only range from -2 to +3. So we pad the rest of the matrix with zeros. What are we left with? It's this infinite matrix of now just normal real numbers, not polynomials anymore, which is periodic and basically consists of a thick diagonal band, and the rest is all zeros. That's the unfolding of a loop. And we're going to use this unfolding to define a notion of total non-negativity for loops. Perhaps unsurprisingly, that notion is a loop isn't totally non-negative if its unfolding is totally non-negative. Since we don't have necessarily an appropriate notion of non-negativity for polynomials, we just use the one for numbers and import it into the loop context. Now I'm going to try to justify this notion of a loop via a couple of remarks. The first is why are they called loops? I don't have a great explanation for this, but I have a bit of a hand-wavy explanation. Namely, you can think about a loop into a topological space as a continuous map from S1 into that space. And if you want, you can think about these polynomials as maps from an interval into the set of matrices. So they're loops into the set of matrices, or in the invertible case, they are loops into GLN. The reason I am only restricting my attention to an interval is because you can also do this more generally with Laurent series rather than Laurent polynomials. And in that context, you might need to think about an interval of convergence. But topologically, these are basically maps from a line into a space of matrices. So sure, let's call them loops. That's the best I can do for today. Okay, by the way, you should check for yourself if you want a, well, in my opinion, fun exercise that the unfolding map that I just described preserves multiplication of matrices. That is, if you took two matrices of Laurent polynomials and multiplied them, then unfolded, that's the same as unfolding them first, then multiplying them. This is easiest to do in the 1-by-1 case. Then you are just unfolding a single Laurent polynomial, and something, I don't know, kind of cool will happen. Okay, by the way, that 1-by-1 case is classically studied. So if you take n equals m equals 1, a loop is just a single Laurent polynomial, and it is known that its unfolding will be totally non-negative if and only if that polynomial has positive coefficients and real roots. That non-positivity condition is really spurious here, because if you're a polynomial with positive coefficients and real roots, then those roots are not positive. But yeah, this is basically saying that checking the total non-negativity unfoldings is a way to check for the real rootedness of polynomials. By the way, if you do this with a Laurent series rather than a Laurent polynomial, you get a generalization of the notion of real rooted polynomials called Fourier frequency series, which are well studied both in classical analysis and have a lot of relationships to combinatorics. That's the subject of Brenti's thesis, for example. Okay, the last note here, this is a fact we will need, is that totally non-negative unfoldings have no internal zeros. What I mean by this is that they basically are sort of north and east closed regions within the band. Or they're sort of convex in a sense. If you had a 0 in the middle of your pattern, you could use it to construct a negative 2x2 minor. So all of our patterns that we study for totally non-negative unfoldings will basically, will not have any zeros on the inside. There'll be two periodic paths with a bunch of non-zero entries in between them. Okay, so what did Lam and Pylyavskyy prove about total non-negativity in the loop group context? Well, they introduced cylindrical networks and generalized the Gessel-Lindström-Viennot story. So for us, a cylindrical network is going to be a whole lot like a network, which we saw before, except now, rather than being planar, it's going to be cylindrical. It's possible to draw it on the surface of a can of tomato soup without the edges crossing, which is a slightly more generous notion than being able to draw it on a piece of paper. And the weight matrix of a cylindrical network is going to be defined analogously to the planar case, but now we're going to introduce a parameter called t to keep track of the winding number of a path. So for example, here's our network from before, and I've basically plopped it onto the front of this cylinder, but I've added a couple of special edges. This blue edge has weight 5, and it starts on the front of the cylinder, then moves to the back and comes back around front. I've also added this red edge with weight 1 that starts here, swings around back of the cylinder, and comes to source 3 here. You notice if I were trying to do this in a planar way, there wouldn't really be a good way to make an edge straight from here to here or from here to here without making a crossing. So the cylindricalness allowed us to do that.
For planarness, do we need the arrows to actually point to the right? Can I not curve my line? Like
yeah, you can curve. So I guess that red edge you probably could have fit otherwise, and maybe the blue one. But if, you know, at some point, sure, if I kept adding them, they wouldn't be possible anymore. Yeah. Yeah, good question. Okay, so what does the weight matrix look like now? Well, it looks a lot like it did before, but I've added some stuff to the entries. So before this entry 3, 1 was 0 because there was no way to get from source 3 to sink 1. But now there is a way. I can take this blue edge, which has weight 5, and come around the back of the cylinder. And since I like added to my, I wound around the cylinder, I get an additional factor of t. Now for us, you get a factor of t for each time you cross the bottom edge of the cylinder. And this is oriented in the sense that if you cross it going the other way, from back to front, then you get a factor of t to the minus 1. So for example, to go from source 1 to sink 3, there used to be one normal planar path of weight 2, namely this one. But now there's an additional path, 2 additional paths, which use this red edge to swing around back and end up at sink 3. One that goes straight across and the other that uses this other part of this trapezoid. So since there are 2 paths using that red edge, and this red edge winds around in the opposite direction than the blue one, we get 2 t to the minus 1 added to that entry. And we can do that to the rest of the matrix. Now, what Lam and Pylyavskyy managed to show is that basically everything from the classical invertible story generalizes to this context. So if I'm interested in the polynomial loops into GLN, meaning the ones that satisfy a certain invertibility condition, then those are representable by cylindrical networks with positive weights. In particular, they're generated as a semigroup by the following simple types of generators. So in red here, we have a type of generator that we saw before, a single entry on the super diagonal, and that's represented by basically the same kind of network. We just happen to plop it on a cylinder. But then we get this new kind of one in blue, which has beta t in the bottom left corner. And that's represented because it goes from the last source to the, from the last source to the first sink. It is in the bottom row, first column. And since it has to pass around the back of the cylinder to accomplish this, it gets an additional weight of t, an additional factor of t. And then we can also take the transposes of these generators, winding around the cylinder the other way. And they might not all look similar when I present them in this fashion, but if you were to unfold these generators, periodically, this beta, when we do the unfolding, would actually end up right here, because it has to be in the next block over, because it has a coefficient of t. So it would actually be on the first super diagonal, just above the main diagonal in the unfolding. Similarly here, this delta t inverse would be on the subdiagonal when I unfold things periodically. So these generators, as infinite matrices, do all kind of look the same, which also explains why topologically they also all kind of look the same. Lastly, we have two more generators, which are called shifts. These look like ones on the superdiagonal or subdiagonal, and a t or t inverse in the opposite corner. And they correspond to the cylindrical network where we sort of twist everything by one, like a barber pole or something like that. And again, this sort of twisted network topologically looks just like the original one with the vertices relabeled. That makes sense because these shift matrices, when you unfold them, look like the identity matrix just moved over by one to the right or left, which has no effect on total positivity. You take this infinite matrix and you just shift all the entries over to the left or right, that won't change whether the matrix is totally non-negative or not. So we also have those generators. And since all of them are representable by cylindrical networks, we know that we could get to any invertible loop with a cylindrical network. Well, that's where my result comes in. My result is about the non-invertible, non-square loops. And that's what I'm about to tell you about. But I should pause again here to ask if there are any questions. Okay, let's take a look. So the theorem I managed to prove is that any loop whatsoever is totally non-negative if and only if it's representable by a cylindrical network with positive edge weights. And from here on in, I'm mostly going to be ignoring the finite folded version, and I'm only going to be thinking about these big infinite unfolded matrices. And you can think about them as functions from, integer lattice points to the real numbers, which have a certain periodicity condition, namely that mij is equal to mi plus n, comma j plus m, if the original loop was n by m. So that's how we're going to be thinking about these things. And let's start defining some key pieces of these matrices so we can do some manipulations. So a southwest corner of a matrix is going to be an entry of this infinite matrix such that the one to the left and the one below it are both 0. So it belongs to, it literally is in the southwest corner of the pattern. And we're going to call it special if the entry mi minus 1, j minus 1 is also 0. So pictorially, that would look like this. Here's a special southwest corner. You should think about it as being the lowest southwest corner after like a long overhang. In other words, it has this sort of long vertical drop, and then it's the last one. It's not a short vertical drop. So for example, here's another 1 by 2 loop. This one actually has no special southwest corners. All of them don't lie at the end of a long overhang. They only are at the end of a overhang of length 1. So for that reason, we call them not special, because I can't think of a different adjective. Okay, fine. So I've told you what a special southwest corner is. Who cares? Well, let me tell you a couple of things. First, I claim that if your loop has more rows than it does columns, then you're definitely going to have a special southwest corner. And that's basically a pigeonhole principle argument. If you suppose you're n by m, so in this case, we are coming from a 3 by 2 loop, you can argue that if you look at the set of columns where the leftmost non-zero entry in each row is, then I claim it has to be, in this case, 2 columns in a row, or in general, m columns in a row. The idea being that otherwise you could argue that there is an internal zero. So here, for example, this missing entry, even though it doesn't look that internal, is an internal zero, because we could still construct this negative 2 by 2 minor using it. So we claim that this will not happen. You will not have the starts of your rows in 1, 2, 3 different columns. They will be in only 2 columns. And it follows by the pigeonhole principle, since there are more rows than there are columns, that 2 of these entries will have to start having non-zero. 2 of the rows will start to have non-zero entries in the same column. And that's exactly what a special southwest corner is. This is just guaranteeing that the move I'm about to describe is possible when m is less than n. Because here's my key lemma. I claim that if you start with a totally non-negative loop and you eliminate a special southwest corner by row operations, then the resulting matrix is still totally non-negative. So I'm going to tell you a little bit about what exactly that means and why it would suffice to prove the result. So here's that statement again. And here's why it would suffice to prove our result. So here's what we're doing. I'm zooming in on my matrix and I'm finding 2 rows, this one with entries B0 and so on, this one with entries A0 and so on, finding 2 rows that start having non-zero entries at the same time. And I'm letting C be the ratio of their first non-zero entries, and I'm using that to cancel out the special southwest corner, the end of the overhang. That's the row operation I'm doing. And I claim that this will actually prove the result. Row operations are realized by one of those simple matrices that we described earlier, one of the semigroup generators with a minus C as the entry. But the inverse is the same matrix with a C as the parameter. So I get this recursion that my original matrix is equal to this simple row operation matrix times something else, which is still totally non-negative. So inductively, I'm trying to see if I can represent my original matrix by a cylindrical network. And I realize, well, I can peel off a piece of that matrix that definitely does have a cylindrical network corresponding to it, and then multiply by something with strictly fewer southwest corners. And as I eliminate them, I will eventually be left with an n by 1 loop of constants, some non-square matrix at the end of the day. And that thing, you can argue, it's not very difficult to argue that a loop of constants is totally non-negative. Okay, and I should mention here that the southwest corners existing only worked for m strictly less than m. But since the matrix is totally non-negative, if and only if its transpose is, we can just transpose the argument to work for matrices which have more columns than rows. The square case requires a little bit of a special trick, but it's also doable. Okay. By the way, I would never want to eliminate Southwest in real life. I personally am a fan of their unconventional approach to the boarding process, although not everybody is. You should prepare yourself for the first time you book a flight on Southwest Airlines. Boarding will be different. Okay, so we've seen that all we really need to do is eliminate a special Southwest corner via row operations and stay totally positive. If we can do that, the rest is going to work for free. That's the hard part, though. Row operations with subtraction do not preserve total non-negativity in general. I mean, positive row operations do, but negative ones don't, because they, for one thing, they could in principle introduce negative entries, but also they put minus signs everywhere and could introduce a negative value overall. But luckily, what I'm going to do with the rest of the talk basically is show you how to use some trickery to get around that fact. So here's my matrix, which has been row operated on. And I want you to imagine as an example that I wanted to compute the minor, this 3 by 3 minor. I could apply the multilinearity of the determinant in rows to turn it into a difference of 2 minors like this. Then remembering that the number C was defined as a ratio of A0 over B0, I could multiply through by a constant, which will, of course, preserve the sign, whatever the sign of this expression is, to get an expression which looks like this. And this expression, besides looking vaguely like an American flag, might not mean much to you, but here's what I claim is special about it. It is a signed sum of complementary minors of a submatrix of M. So here I've grabbed some submatrix of the original guy, which I know is totally positive. And I claim that we've taken some complementary minors of it in the following sense. Two minors are complementary if the row set of one is the complement of the row set of the other, and similarly for the columns. So for example, here, this blue 3x3 is a minor over here using columns 2, 3, and 4, and rows 1, 2, and 4. And it's getting multiplied by this constant B naught, which is the minor formed by taking the complement of the column set, so just column 1, and the complement of the row set, just row 3. Similarly here, this red expression is obtained as a product of complementary minors of the original guy. This doesn't help us yet because the complementary minors in the original matrix are non-negative on their own, but we're subtracting them. So we're not out of the woods yet. We're gonna have to do something special. So let me show you what that special thing is. So yes, this is me just more formally defining what a complementary minor is. If A is an L by L matrix, then it looks something like this: A ij times A L minus I, L minus j. And what we've managed to show, or I have managed to prove elsewhere, is that the minors of M prime, this row operated matrix, can be written as signed expressions in the complementary minors of M. And our goal for the rest of today is to show that they cancel. To do so, we're going to introduce some pictures. The complementary minor diagram, I should mention that this was introduced by Rhodes and Skandera. The complementary minor diagram is basically going to be a pictorial way to record a complementary minor, or a pictorial way to record a pair of sets I and j that are the same size. How do we do it? Well, here's a vague description. For each element of j, the column set, place a black dot on the left. For each element of I, the row set, place a white dot on the right. It's not very clear what that means, so let me show you an example. If L was equal to 5, I, the row set, was 1, 2, 4, and j was a set 1, 3, 5, you would get this picture. So let's look on the left side. I have black dots in positions 1, 3, and 5. That's because my set j was 1, 3, 5. On the right, I have white dots in positions 1, 2, and 4, because my row set I was 1, 2, and 4. And the rest of the dots are the opposite color by default. And this picture, although in a very strange way, records precisely the information of the dimension of a matrix and a row set and a column set. So if I wanted to, rather than telling you to take like this complementary minor corresponding to I and j, I could just hand you this picture as a fun little puzzle, and you'd be able to figure out the corresponding product of complementary minors. So we're going to allow ourselves to do that because it will make the combinatorics more pleasant. So if you wanted to compute this product of complementary minors, I could instead just have handed you this picture of dots which are white and black. And in particular, if we can all agree on what matrix we're using, I won't even write the name of the matrix A. So what you should think to yourself is, funny little picture with black and white dots plus totally non-negative matrix equals positive number. This is some combinatorial description of a positive number that you can obtain from a totally non-negative matrix. Okay, we're going to do it again. I'm going to draw another funny little picture which describes the process for getting a positive number out of a totally non-negative matrix. This one's going to be more complicated, and I'm going to have to talk about it kind of fast. So hold on to your hats. Just remember, the moral of the story will be funny little picture plus totally non-negative matrix equals positive number. Okay, so I'm going to tell you about the Temperley-Lieb algebra. The Temperley-Lieb algebra, TLL, is a complex algebra generated by L-1 formal symbols and subject to these relations. They look a lot like the braid relations for the symmetric group algebra. If you're familiar, that's not a coincidence. The Temperley-Lieb algebra is a quotient of the symmetric group algebra. Okay, suppose you don't want to deal with these formal relations and you would rather deal with pictures, you could do this instead. Multiplication in this algebra is realized by concatenating non-crossing matchings up to loops. So let me show you what that means by an example. The ith generator, Ti, corresponds to this picture, which looks a lot like the ones we had on the last slide, but now I've drawn some arcs on it in a way such that they don't cross. And Ti is going to be a picture where there's this sort of elbow hyperbola looking thing in rows I and I plus 1. The Temperley-Lieb algebra TL has L dots on each side, so the generators can only go up to TL minus 1. Can't have an Lth generator because the elbow would need to go to row L plus 1, which we don't have. Okay, so if I want to multiply these generators, what do? I start by multiplying them in the usual way, but then I replace each of them by the corresponding picture. So here I had a T1, T2 squared. I replaced that with this concatenation of the pictures where I had elbows in row 1, then in row 2, then in row 2 again. And similarly here, I had them in row 1, row 2, row 3 and 4. I guess rather than T4, that should have been a T3. Okay, then what do we do? Once we've concatenated them, you sort of grab the ropes from either end and pull them tight. And if there happen to be any loops, like this one, sitting in your picture, each of them contributes a factor of 2. So in this case, after I pull these diagrams tight, I'm going to get a factor of 2 here. And now these pictures don't look like our original ones. That's because the algebra generators with these elbows are not a linear basis of the Temperley-Lieb algebra. If you want a linear basis, you have to consider all possible non-crossing matchings on 2L points. So when L equals 3, for example, here's a linear basis, the Temperley-Lieb algebra, and includes our 2 algebra generators, but also some other fun pictures. You might remember that the number of non-crossing matchings on 2L points is given by the Lth Catalan number. So the Temperley-Lieb algebra as a vector space has dimension equal to the Catalan number. And that's how I want you to think about an element of the Temperley-Lieb algebra. It's some formal sum of these Catalan-like objects. Okay, what are we going to do with them? This is the part where we take funny picture plus matrix equals number. Okay, so what do? If I gave you a basis element of the Temperley-Lieb algebra, in other words, a non-crossing matching, and a permutation of L things, here's what I want you to do. Write down a reduced word for that permutation, and then spit out a real number in the following way. If your reduced word was SI1, SI2, up to SIK, you should replace each SI with a TI minus 1. So SI, these are the adjacent transpositions for the symmetric group. The TIs are the generators of the Temperley-Lieb algebra. So replace the adjacent transpositions with the corresponding generator of the Temperley-Lieb algebra minus 1. So I've given you a permutation. Form this expression, simplify it down using the rules on the previous page. Hopefully I've convinced you that it's at least possible, even if it's not easy. Then look for the coefficient of the non-crossing matching that you were interested in and grab that real number. That's what the function phi t of w is. Is it complicated? Yes. All you need to know is that it takes matching plus permutation and spits out a real number. And we could use this function to create a determinant-like function on matrices called the Temperley-Lieb immanent. Temperley-Lieb immanent, its definition looks a whole lot like the definition of the determinant with the following key difference. The sign of the permutation has been replaced with this funny phi coefficient function. So in this way, you could take any non-crossing matching, do all of this business, and what you'd end up with is some determinant-like function on matrices. And that's all you should think about for now. I'm not even going to compute an example. If you gave me some non-crossing matching, I could apply it to a matrix and get a number. So from now on, rather than writing IMT or all of this stuff, we're just going to draw the picture of the non-crossing matching, and we'll all agree that it means some real number you could in principle compute. And here are some cool things about those numbers. First of all, if you start with a totally non-negative matrix, then a Temperley-Lieb immanent evaluated on it will also be non-negative. This is highly non-obvious, and a pretty cool result. Additionally, there is a relationship between Temperley-Lieb immanents and complementary minors. Namely, if I give you a complementary minor diagram like I have here on the left, some colored array of dots, then it is equal to a sum of Temperley-Lieb immanents. Which ones? It's the ones that connect white dots to black dots in the complementary minor diagram. So complementary minors expand positively into Temperley-Lieb immanents. And I want to note here that the coloring of the dots does not affect their value. The coloring of the dots on a Temperley-Lieb immanent is just a bookkeeping device to help us remember which complementary minor did this Temperley-Lieb immanent come from. So now we've got two different funny pictures we can draw, one without lines, one with lines. But the key takeaway is that they are ways of getting a non-negative number out of a totally non-negative matrix. And we're still not out of the woods just yet, because the Temperley-Lieb immanents are themselves non-negative, and they are the building blocks for the complementary minors. But we have some complementary minors that appear with negative sign, which means that in the expressions we're interested in, there are Temperley-Lieb immanents with negative sign. So all of this complication hasn't bought us anything yet, but what it has done is allowed us to view the interactions between complementary minors via the combinatorics of these non-crossing matchings, which is the part that matters. So I'm going to show you an example of how you can use these non-crossing matchings to figure out that a minor of the matrix we're interested in is positive. And if you want the full detail, you can find it either in the current version of my paper or in the better version, which should appear before too long. So let's do an example to finish things off. So let's suppose this is my row operated on matrix. And I didn't say it explicitly earlier, but when we do these row operations, we do them periodically. So there could be multiple copies of rows with operations being done on them. And let's suppose I wanted to compute this minor and check that it is positive. I start by expanding via multilinearity and multiplying by a constant until I get something that looks kind of like what we had before. And I argue that this expression is a signed sum of complementary minors of a submatrix of M. So let's pull up the non-row operated on version of the matrix, and let's see how every product here is actually a complementary minor of the original guy. So here's this first one, and we can draw the corresponding diagram. Here's the second one, just corresponds to a little bit of a flip here in the rows and columns, and here's the corresponding diagram. Similar for the other two, we can realize them as complementary minors inside of the original matrix and draw their diagrams. What we're left with is a signed sum of complementary minors of a matrix which we know is totally positive. So let's argue that this signed sum has to be non-negative, and we'll be done. Here it is. I'm going to apply that theorem, which transforms each of these complementary minors into a signed sum of the corresponding Temperley-Lieb immanents. We get this very complicated sum with pluses and minuses, but what it's done is it's refined things so that I can do cancellation. So remember that the color of the dots does not affect the value of the immanent. So as long as they have the same shape, I can cancel them out. For example, this guy right here, the first one with the negative sign, will cancel with this one right here. And I've decided to record the cancellation with travel essentials. So let's put an umbrella on those, they're matching, and a backpack on those two, and just keep track of the cancellations that we find. And most of them are going to go away. But unfortunately, even after cancellation, we're left with two terms of strictly negative sign. And these Temperley-Lieb immanents are non-negative, so that is a problem. However, for my final trick, I claim that these immanents with negative sign are not just smaller than the positive one, they're actually zero, identically. How do we argue that? Well, we first remember which submatrix of the original guy we were working with. And then we notice that these Temperley-Lieb immanents could have come from a different complementary minor. Sometimes the same Temperley-Lieb immanent appears from multiple complementary minors. In this case, here are the row and column sets of these transformed versions. And I claim that, for example, this one, which comes from the row set of I equals 3, 4, and the column set of j equals 1, 2, is actually corresponding to a product of complementary minors, which is 0. This one. So this product of complementary minors expands non-negatively into Temperley-Lieb immanents, and each of the Temperley-Lieb immanents is itself non-negative. So if the whole sum is 0, and it's a sum of a bunch of non-negative things, each of those Temperley-Lieb immanents individually must be 0. So we could use this lemma to claim that this Temperley-Lieb immanent is actually 0. Similarly with this other one, they're both 0, so they are dead. And the only remaining Temperley-Lieb immanent is this one with a positive coefficient, and it evaluates non-negatively on totally non-negative matrices. So that's how the proof goes. In general, I break it down into combinatorics of the cases of these symbols, and you can see that in the current archive version, but it will be better, sorry, in the new version. But that's it for now. So thank you for listening, and I can take some questions.
I think I have the first question.
Okay.
Is a dead fish part of your travel essentials?
No, you should not take a dead fish with you. They're gone. They're 0.
Okay. But a rubber duck is a travel essential.
Of course.
Absolutely.
I have one.
Yeah.
Is there any version of this story with non-integer weights and positivity in the cone of, positive cone of some ring of bases?
Well, the matrices I have been showing you could have non-integer weights. For example, when we do that row operation, we take like A0 over B0 as our weight, and that could be like any real number.
Oh, I mean like X0 as non-numerical weights. Sorry. Yeah.
Oh, absolutely. So if you were to apply the Gessel-Lindström-Viennot lemma to a particular matrix who has variables as its weights, you could recover the Jacobi-Trudy identity, for example. And this guy, Alan Sokol, has studied generalizations of this stuff to any partially ordered commutative ring. A lot of these results will generalize to that context. And some stuff I've been working on recently, for example, would study, there's like a big conjecture in the Chow rings of matroid world about a version of this, unfolded non-negativity, where rather than real numbers, you have genuine group representations. And you ask that the minors of this matrix are also genuine group representations, not virtual characters. So yeah, there are lots of generalizations of this story.
Cool. Yeah, I'll probably check this out.
Yeah. I should say that latter notion is not well studied yet. I'm going to get there, but it's related to like causality, if you've heard about that in commutative algebra. It's some pretty cool stuff.
I have a question that, it isn't really a question about the material of this talk, but when you were defining the immanents, you had some function that you were purposely keeping vague.
Yeah.
Let's
find it.
That, takes a permutation, and I believe it was a non-crossing diagram, and, came up with a positive number, or came up with a number.
Mm-hmm.
And so the way it took a permutation is it took a reduced word for that permutation. And it was somewhat surprising for me that this function apparently worked on any reduced word. Is that an interesting story?
Yeah, so it's not obvious that it doesn't depend on the reduced word, but it doesn't. And it basically comes from the fact that the Temperley-Lieb algebra is a quotient of the symmetric group algebra.
Okay.
So the relations among the TIs are like sort of act a little bit like the relations among the SIs, and you can show that this will work. Yeah.
Okay.
Yeah, you're right. I did sweep that under the rug. Or maybe the value of a Temperley-Lieb immanent is just random. I don't know. I don't actually compute them that often. I don't want to. As long as it's positive, that's what matters.
I had a question about this positivity. You said it's non-obvious that this quantity is always non-negative. Has it ever been applied to show the non-negativity of something that was maybe conjectured to be non-negative in a different context, and it rather surprisingly turned out to be a Temperley-Lieb immanent of some sort? I guess I'm asking what has been an application of this non-negativity?
Yeah, good question. So these haven't been used that many times yet. So besides the one you saw today, applications of Temperley-Lieb immanence. I want to make sure I'm quoting this right, but I believe Temperley-Lieb immanents are a proper subset of the Kazhdan-Lustig immanents. So they've appeared in that context as sort of another combinatorial description of Kazhdan-Lustig immanents. And they also, there is some conjecture that that maybe all non-negative immanents have something to do with Temperley-Lieb immanents. Like maybe they're all positive expressions in Temperley-Lieb immanents or something like that. Like they're all elements of Lustig's canonical basis. So they have appeared. I don't understand that story very well, but yeah, I think that's the best I can do for now. Oh, there is a paper which applies them directly to sure positivity, which I could send you.
Interesting.
By Pasha and Losnikov. I can find it in the chat if you stay for another moment. Here it is. So here's a paper which applies Temperley-Lieb immanence to sure positivity.
Okay, so it's that one, right? Right.
Yeah.
Very cool. Thanks for the talk. It was very interesting results, and I love the pictures and the slides. Very creative stuff, you know.
Oh, thank you.
Yeah.
The key is Keynote. I have abandoned Beamer, and I'm never going back.
I think that's the way forward. You know, I think I'm sick of Beamer as well.
Yeah, just drag and drop. Why should I fiddle with code? I cannot tell you how many hours it would have taken otherwise.
All right. Okay, I've got to get on this train then. Fine.
Yeah. I tried to do it in PowerPoint, but my University of Minnesota PowerPoint subscription does not allow add-ons for LaTeX. So Keynote it is for now.
I recently saw a PowerPoint talk that far exceeded the Beamer ones that I've usually seen. I don't know. I feel like the Beamer ones have gotten boring, you know.
Yeah.
Predictable.
I mean, the Beamer ones, they all look the same. Maybe we should stop the recording before we get too crazy.
Oh, I'm happy to be on record as saying that I prefer
Keynote.
Too.
Before we get cancelled for dissing Beamer.
Yeah, look, you guys can keep using Beamer. But maybe with